Welcome to the Explainer. So today we're looking at something that might seem, well, totally mundane at first glance. A puddle of wet concrete. But we're going to treat it like a high-stakes forensic toolkit. We are decoding the CSA A23.2-2019 standard. This is the exact method engineers use to analyze a simple puddle of self-consolidating concrete to actually predict the structural integrity of massive skyscrapers. If you've ever wondered how builders can guarantee that a foundation won't fail, the secret is hiding right there on the ground, before the concrete even cures.
Okay, let's grab our detective's notepad and run through the game plan. We'll cover the science of slump, setting up our test, the incredibly tight 3-minute procedure, measuring spread and speed, and finally, the visual stability index. Let's get right into it. Kicking things off with Section 1, the science of slump. Because before we test anything, we've got to understand the unique behavior of this material. So we're dealing with self-consolidating concrete, or SCC. Now, you know this isn't your standard thick driveway mix. It is highly flowable, meant to spread perfectly into place and wrap around complex steel rebar entirely on its own. Literally no mechanical vibration or tamping required. But this concrete requires a really delicate Goldilocks balance. It has to be incredibly fluid to travel through that complex formwork, but stable enough that its heavy, coarse aggregates don't just sink straight to the bottom. It's kind of like chocolate chips sinking in a really thin cake batter. You absolutely don't want that. And this illustrates the core conflict we're testing for. We are essentially measuring two competing forces, slump flow versus stability. On one hand, slump flow is testing the unconfined fluidity, how far and how easily the concrete can travel horizontally. But on the other hand, we have stability, which is the concrete's ability to resist the segregation of its paste from its heavy rock aggregates. Think about it. If it flows great but separates, the structure fails. If it's stable but too thick, it won't fill the forms. We absolutely need both. Moving right along to Section 2, setting up the test. As you might expect, the standard dictates some highly specific constraints before we even pour a single drop. First up, the magic number 28. This test only applies to concrete with coarse aggregates up to 28 millimeters in size. That is a hard limit set by the standard. If your concrete mix contains rocks larger than 28 millimeters, you can't just test it as is. Those larger aggregates actually have to be meticulously wet sieved out beforehand to ensure the slump flow mechanics aren't artificially disrupted by oversized chunks. Then we've got the number 10. And this is where the drama really hits the site setup. You have exactly 10 minutes to complete this test from the second you obtain the sample. That 10-minute window includes transportation and any remixing of the sample. It demands absolute efficiency. For the testing technician, there is zero time to go hunting around for a lost trowel once that sample is pulled. The clock is running. With that 10-minute clock ticking away in the background, we jump into Section 3, the 3-minute procedure. This is the critical window where the physical handling of the concrete must be flawless. So, you've got a maximum of 3 minutes from filling to lifting. First, dampen your base and center the cone. Second, fill it in a single continuous lift. And remember, absolutely no rotting or tamping. Third, strike off the top. But the absolute make or break moment is step 4, lifting the cone. You must raise it exactly 225 millimeters in a steady 3-second upward lift. Literally 3 seconds, give or take one. Twist it or shake it in those 3 seconds, boom, you completely ruin the evidence and invalidate the entire test. Once you pull that mold perfectly straight up and the concrete spills out, we hit Section 4, measuring spread and speed. It's time to profile exactly how our suspect behaves. What's actually super fascinating here is how we capture two totally different metrics from this one single action. First, we get the slump flow, which is the final resting spread calculated by averaging 2 perpendicular diameter measurements, but we also measure the T50 time. Now, this requires 2 people, one lifting the cone and one holding a stopwatch. You start the clock the exact millisecond the mold releases the concrete, and stop it the moment the flowing edge hits a 500 millimeter diameter circle scribed on the baseboard. This T50 time is a brilliant secondary indication of viscosity, showing us not just how far the mix travels, but how fast and flowable it truly is. But hey, you absolutely cannot rush the final measurement. You gotta let the concrete completely finish its journey. Let it completely stop spreading, or wait a maximum of 2 minutes before taking your tape measure to it. You measure the widest diameter, and then you measure a second diameter exactly 90 degrees perpendicular to the first. And here's the kicker. If those 2 diameters differ by more than 50 millimeters, the spread is way too asymmetrical. The standard says you must scrap it and repeat the entire test.
Assuming our spread is nice and uniform, we finally arrive at the climax of this whole investigation. Section 5, the Visual Stability Index. This is where we read the clues left behind.
When you're staring down at the edge of that puddle, the absolute most critical clue you're hunting for is called the halo. A halo is this watery ring of cement paste or mortar that has bled away from the racks and formed around the outside circumference of the slump flow. If you see this, it's a major red flag indicating a dangerous separation of ingredients. The paste is essentially running away, leaving the structural aggregates behind in a pile. And by the way, if a halo is present, the standard explicitly dictates it must be included as part of your total diameter measurement. And that brings us to the visual grading. The technician subjectively grades the puddle using the Visual Stability Index, or VSI. A 0, flawless, no segregation, no bleeding. A 1 is totally acceptable with just slight bleeding. But hit a 2, and you've got trouble with noticeable halos. And a VSI of 3, that's a catastrophic failure. You'll see a massive mortar halo and a huge pile of rocks left sitting dead in the center. The mix is completely unstable. Finally, the whole shebang gets locked down in the official report. All of these forensic clues, from the exact horizontal spread to the nearest 10 millimeters, the T50 speed to the nearest second, that subjective VSI grade, and the presence of any halo, they are all meticulously documented. This mandatory reporting by a certified technician is exactly what assures the architects and structural engineers that the concrete flowing into their hidden formwork will actually hold the building up for decades to come. It honestly completely changes how you look at the built environment, doesn't it? The structural integrity of massive towers literally comes down to certified technicians analyzing how wet concrete spreads across a piece of plastic. Thanks for joining me on this explainer. The next time you walk past a construction site, you've got to ask yourself, what secrets are hiding in their concrete puddles?